today. It is Halloween, I guess. So we'll be talking about seismic inversion. And this is the terms of use. Essentially, this material is only intended for students or those who professionally teach students at the college, university, junior college level. The objectives, I'll be talking about the comparison between zero phase and impedance data. The I'll talk about our ultimate goal, what relative impedance is, what absolute impedance is, how we get a low frequency component for the seismic data, and then the basic inversion process. So as a quick review, if we have a stack of lithology, such as shown on the left, if we generate zero phase data, what we will see is at some of the major impedance boundaries, a peak or a trough. And so the zero phase data is good at detecting boundaries between different impedance zones. What relative impedance does is it tries to give us peaks or troughs related to intervals that are associated with these boundaries. So on the relative impedance trace, we have a trough that's characterizing the marine shale above the purple or magenta boundary. We have a peak that's characterizing the upper part of this shore face sand, and so on and so forth. So zero phase is great for mapping major changes in impedance boundaries. The relative impedance is used more to try to quantify properties above or below one of these impedance boundaries. I've already talked about forward seismic modeling. It's how we generate our synthetic seismograms. And so we have some block logs, velocity and density. We can calculate what the reflection coefficients are. We could use a process called convolution to convolve the wavelet with the reflection coefficient series, and that gives us our modeled or idealized or synthetic seismic trace. And when we have a forward model such as this, we get a unique solution. So the input is sonic and density. We need a seismic pulse. This is performed at well locations where we have the necessary well logs, and it allows us to tie well markers, formation tops, faults, other pieces of information from the well log to the seismic trace. And the well data that we have, we can modify it so that we can look at what sort of seismic signature we would have if the reservoir was to change thickness, as one example. Seismic inversion, so I have the convolution operator with the -1 to indicate it's an inversion process. We begin with the actual seismic trace. We supply a wavelet, and what we're trying to get back to is blocked impedance. What sort of impedance structure, series of reflection coefficients could have generated the actual trace. And we can take that one step further and try to break it into a blocked velocity log and a blocked density log. And whenever we do inverse modeling, the solutions are non-unique. There's more than one way to generate this seismic trace. So the input again is a seismic trace. It's performed at a well location, and also we can do it away from well locations, essentially at any location where we have a seismic trace. The well data can be used to try to calibrate the results, and it can help us understand what the seismic is telling us about the rock properties as we move away from the drilled locations. And we have a variety of software that we can use to generate multiple realizations of what that velocity and density structure is at each seismic trace. So our ultimate goal, we would like to turn each seismic trace into an impedance trace. giving us further information about the velocity and density. That would allow us to make better predictions about rock properties in our interval of interest, say our reservoir zone, rather than acoustic properties at the major rock boundaries. And the variations in the velocity and density at each trace can be better indicators that we might have some lateral changes in rock property, such as the thickness of the reservoir, the net to gross of the reservoir, or the porosity of the reservoir. So definition, seismic inversion is the process that starts with reflection amplitude trace, generates a model for the impedance structure that produced that seismic trace, and then transforms the impedance into estimates of the P wave velocity v sub P, the S wave velocity v sub S, and density. It's an inverse of the convolution method that we use to generate synthetic or modeled seismic traces given well logs at a well location. So let's talk a little bit about relative impedance. We start with zero phase trace data, and that zero phase seismic has limited frequency range. And so when we derive an impedance estimate, a relative impedance, that's going to have the same limitation in the frequency domain. It's relatively easy to derive zero phase, to derive relative impedance from zero phase. One way is to integrate the zero phase trace. Integration would be similar to a running sum. The other option is to rotate zero phase data by minus 90 degrees. And so if I have a zero phase trace, I could use either trace integration and get relative impedance, or I could use a phase rotation minus 90 degrees to get a relative impedance trace. So the major difference, here's an impedance log for a well based on this reference. And this is the relative impedance that has been calculated. And what's the main difference is that there's some lower frequency variations in impedance that we don't see in relative impedance. So relative impedance data lacks the low frequency trends, and it also lacks the high frequency oscillations that we see on the impedance log itself. We're not so much interested in the high frequency, but we would like to try to restore the low frequency information. And if we can do that, instead of relative impedance, if we add in low frequency, we can get what's called absolute frequency. So as I mentioned, there's bad limitations in the zero phase data. And so that only gives us an approximation of acoustic impedance. If we can go the extra step and restore the missing frequencies, usually less than 10 hertz, then we can get what's called an absolute impedance, which gives us a better fit to the actual impedance log data at our well locations. So the sonic and density logs have a wide range of frequencies from 0 out to 200 or more hertz. The zero phase data has a frequency range of maybe 10 to 50 hertz. And so the relative impedance is also going to be band limited to 10 to 50 hertz. So we do talk about two types of impedance. I've already been mentioning these: relative acoustic impedance. I also mentioned that we can get that by a simple mathematical integration, or we can do a minus 90 degree phase rotation. The relative acoustic impedance tells us about relative changes, increase in impedance or decrease in impedance. In some cases, it can be calibrated locally to average physical properties of a reservoir unit, such as porosity or net to gross. It's not useful for accurately measuring vertical impedance changes over large two-way time intervals or depth intervals. With absolute acoustic impedance, we begin with the relative impedance, which I've just talked about. we get an estimate of what the low frequency component of the seismic data is. We can get that from well data within our study area, our project area, or we can get velocity data from our stacked analysis of the stacks to try to get a stacking velocity that comes to us via our seismic data processors. We can do a precise calibration of impedance measurements from multiple reservoirs at multiple well locations, given enough well control. And frequently, the absolute impedance is used to build input for detailed reservoir models, such as the models that we need to do a reservoir simulation. So the low frequencies can come from stacking velocities. So here we have a semblance diagram. It's for one trace, and we're looking at two-way time, a proxy for depth, and we're looking at velocities from slow velocities to high velocities. And the colors here, the hotter the color means the more consistency there is in the stack, the flatter the stack has been. And so a velocity analyst has picked the locations where the blue X's are as defining what the low frequency trend in velocities are. The red line is the interval velocity based on those particular picks where the blue X's are located. And so we can fit a curve through those stacking velocity picks, the blue X's, and that gives us a low frequency trend to the seismic data. So our seismic might have a bandwidth of 10 out to 50 or 55 hertz. We don't have the very high frequencies. We don't have the very low frequencies. We're not so interested in the high frequencies, but we would like to be able to get an estimate of the low frequency. We can get that from our velocity analysis. And also, if we do have impedance logs, sonic and density multiplied together to get us an impedance log at well locations, we can use the available well data to also give us a low frequency component. So the acoustic impedance data estimates the impedance, which is a function of the sonic and the density log responses. We need migrated and stacked seismic data. Acoustic impedance is an interval attribute as opposed to an interface or boundary property. We can use the acoustic impedance data to resolve beds that are thinner than tuning and so get more detailed stratigraphy than with zero phase data. We can use the acoustic impedance data to try to tell us something about lithology or porosity. In some cases, a hydrocarbon water contact will stand out more significantly, more easy to interpret using impedance data than zero phase data. And for those people that worry about predicting pore pressure, acoustic impedance is a very key factor in doing that. So the value of the impedance data, it represents the subsurface better than the zero phase, especially when we can get an estimate of that low frequency and not deal just with relative impedance, but absolute impedance. The low frequency tells us something about the geological variations, and we also get improved vertical resolution. It may yield us better estimates of reservoir thickness. It can be transformed into other rock properties such as net pay, porosity, or hydrocarbon pore thickness. We need some well calibration within our study area in order to do that transformation. It allows us to perform enhanced seismic attribute analysis. And increasingly, it's being used by interpreters to delineate reservoir rocks and their surrounding seals, especially away from existing well location. For post-stack inversion, we have a number of assumptions. We assume that the input data has been imaged properly and that it is zero phase data, not minimum phase or mixed phase. We assume that the seismic amplitudes are proportional to the reflection coefficients. so that the processing that has been done is controlled amplitude and controlled phase. The input seismic data represents normal incident or zero offset data. If we do have AVO effects, they can cause a little bit of a problem. I'll talk in a moment about that. Here it is. In order to compensate for this assumption that it's normal incidence, if we have an area where we do have AVO effects, what we'll do is we'll do the inversion on the near stack so that we don't get as much of an impact of amplitude versus offset. And that assumes that the near stack has enough signal and noise that we get good quality data. Another assumption is that we don't have multiples or coherent noise, and so hopefully our processors have been able to eliminate both the multiples and the coherent noise. And we need an approximate wavelet, and we assume that what we've extracted is appropriate and does not vary too significantly as a function of two-way time. So we'll take our seismic data that should be zero phase data. If we know it's not zero phase, we can rotate it to zero phase. We can use full stacks if we don't have AVO in our study area, or we can use a near stack if we do. And then we need an estimate of the stacking velocities that typically is done with normal seismic data processing. The well data, we have sonic and density logs, we have markers, we can have check shots, and ultimately what we'll do is we'll combine the seismic and the well data to get a series of mapped horizons. We can then get from the stacking velocities a low frequency component for the seismic. We can filter the sonic and density logs to get a low frequency component at the well locations. We can merge those two. We need to extract a wavelet from the seismic data, and then we can perform the inversion by using the extracted wavelet, the low frequency, the zero phase data, and the low frequency component of seismic that we get either from stacking velocities or filtered logs or a combination of the two. And when we do the inversion, we may take it a step further and try to solve for P impedance, for density, and for S impedance. So that's the basic process that we will use to get inverted data. And from the P impedance, the density, the S impedance, what we'll try to interpret is what the lithology is and or what the porosity of the sandier units or the reservoir prone units are. So have a couple of examples, and I always think I think it's a Chinese proverb, one picture is worth 1,000 words, is appropriate. So here we have zero phase data. We have a little bit of an anticline here, and we have a higher amplitude response, and that's associated with the presence of gas. If we zoom that in, here's the top of the reservoir, horizon 2, and where it's filled with gas, we get an anomalously high peak and trough. Here it is again zoomed in, the zero phase data. We use seismic inversion, and we can get this type of display where the lower impedance are in the purples to blues, and the mids are in the oranges and yellows, and the highs are in green. And you see this kind of aqua blue is a relatively low impedance compared to the surrounding orange and red. And so we go from very high impedance into moderate and low impedance back into higher impedance. And so this low impedance is caused by the presence of gas in the reservoir. Another example, zero phase data. In this case, we have one well at this location, another well at this location. The black blocked log is impedance, and the purple arrows are showing some low impedance zones. Not too simple on the zero phase data to figure out where the low impedance zones are. we do inversion, and now we have color-coded impedance. Low in this case is green to yellow, moderate is red, and high is blues and purples. And so we see this streak of green here is this low impedance zone, which seems to correlate to this low impedance zone. This kind of yellow-red is a second low impedance zone, and this green-yellow is a third low impedance zone. And so much easier to see details and understand where the low impedance, which could be due to the presence of hydrocarbons, is with the lower section than the zero phase data in the upper section. And here again is the P wave velocity, and this is an estimate of the density. And they're using probabilistic neural network analysis in order to generate these. So the previous slide, I'll go up one. This is the impedance, and then the impedance was broken into an estimate of P velocity and density. And so that gives us some more information about the extent of the low impedance zones that could be associated with hydrocarbons. So acoustic impedance provides a log estimate at every single seismic trace as to what the impedance structure is, and by inference what the velocities and densities are doing. Intervals are easier to interpret geologically than using interface property data that the zero phase data represents. The estimated acoustic impedance can be compared to the well-derived acoustic impedance to try to do some calibrations and understand what increases and decreases in impedance represent. Acoustic impedance can help us estimate lithology or porosity or fluid content, or help in our prediction of pore pressure. And the inversion process attempts to remove the band limiting effect of the seismic wavelet, hopefully providing us with increased geological detail. And we can use geostatistical data from our well information, combine that with seismic impedance, and produce acoustic impedance volumes with greatly improved vertical resolution. Here are the references to some of the images that appeared in this lecture, and those are available for you to look up and read more about. And if you do the exercise associated with Unit 29, what you'll start out with is a relative impedance trace versus two-way travel time, a low frequency component to that. You'll have the numbers associated with the red curve and the blue curve as a function of two-way travel time depth. And what you'll do is you'll calculate what the absolute impedance is. And so you'll see, or you'll go through the mechanics involved in combining a low frequency estimate with the normal frequency content of the seismic to try to get an absolute impedance estimate. So I think that wraps up the prepared statements for this. We have some time for some questions.
Great. Thanks so much, Fred. The audio was on my end. You sounded very clear, so I don't know how I'm sounding now. We currently no questions, but as Fred has put up the schedule, so we're doing the seismic inversion one now at 1 p.m. You can join us again at 2 p.m. for the estimated recovery lecture. Followed next week, we have a lecture on it's only Tuesday. We have a lecture come Thursday and a lecture on next Tuesday, and then we're doing two on the following Thursday. So in the next 2 weeks, we'll be wrapping everything up. And yeah, so there still hasn't been any questions, Fred. So with that, I ask you guys to join us again here at 2 p.m. and 2 p.m. Eastern time, and join us for the estimated talk. All right, bye everyone.
Thanks everyone for tuning in.
Hi.
Bye-bye.
Bye.